us are here. We've made it through the week. We're going to start the last session of this wonderful conference. And our first speaker is Eva Pavarini. She's going to talk about finding through Kugel-Khomskii systems. Eva is from the Institute for Advanced Simulation at Forschungszentrum Jülich. Eva, please.
Okay, so I can start. I hope you hear me well. Let me start by thanking Marcelo, Carol, Teresa, and Valber for inviting me to this very nice conference. And I'm really sorry that I cannot be there due to some consequence of an accident I had some months ago. But I'm nevertheless very happy to being able to present some of our recent results on Kugel-Khomskii systems. So we discussed that. The pointer is now gone. Okay. Maybe I don't need it right now. Yeah, so the talk is about finding through Kugel-Khomskii system, something which has been an interest of mine since a long time. And in the last 2 years, we could finally pin down some material in which true Kugel-Khomskii effect can be seen, while in many others we had shown along the years that although they were believed to be Kugel-Khomskii system, this was not actually the case. And I want to tell you about this story. Maybe I exit from this mode so I can use the pointer. Do you see my slide well? Ah, maybe this one. No, the pointer is gone. Okay, nevertheless. Yeah, so, okay. Yeah, so let me start from the very beginning, because perhaps not everyone is familiar with the Kugel-Khomskii model, particularly younger people in the audience. This is something which was introduced 50 years ago. Actually, I realized that it's the 50th birthday of this famous paper of Kugel-Khomskii, where it was presented the idea that if you have a strongly correlated material with orbital degrees of freedom, there is a purely electronic mechanism which can lead to orbital ordering via superexchange. And at that time, the materials which were mentioned by Kugel and Khomskii were potassium, copper, fluoride, and lanthanum manganese. These are the two main systems discussed in the paper. And they became very soon the example, the considered textbook example of orbital ordering. So since then, orbital physics and all what arises from the Kugel-Khomskii model became some fundamental field in the field in strong correlation physics. So the idea is simple. If you have a strongly correlated oxide, this is in first approximation described by the Hubbard model with orbital indices. And these orbital indices are such that, well, I need a pointer, that when you consider the Hoping integral as a perturbation, you actually then can map this model into an effective superchange interaction, which is made by many terms. The first is the normal magnetic exchange, where the coupling is proportional to square over u. And then there are additional terms which involves the orbitals and our interaction between pseudospin, which play the role of spins in orbital space. And there is also spin-orbit interaction. And all these coupling are somehow of order t squared over u. And in the same way as we can have magnetic interactions which give to magnetic order, a well-established feature of strongly correlated materials, well, we can also have orbital interaction which can lead to orbital ordering. This was the key idea, which can lead to order without any static lattice distortion. And as I was saying, from that time, then orbital ordering, Kugel-Khomskii physics exploded, and there are tons of papers which mention either orbital ordering or use the Kugel-Khomskii model to explain and predict new effect in the physics of oxides. And here, these are some of the papers which I collected a few years ago to show how this field became, how this type of phenomena are found everywhere in oxides. But there is not only ordering, of course, there is also more exotic phenomena like orbital liquid theory, which was developed based on the Kugel-Khomskii model. And or a strong orbital fluctuation with frustration in vanadates, or spin orbital entanglement. And in more recent years, there are various attempts. So this is a paper in Conmat from the group of Cavalieri to manipulate orbitals with creating a situation where you can fine-tune the ferromagnetic temperature, for example, in certain materials. So that's all very nice and interesting, but what we were interested in is to find proof that actually these phenomena were somehow arising from this very nice model of Kugel and Khomskii. And so we were interested in going back to the origin and understanding what is the microscopic mechanism. In particular, if now we are in the position of planning of, let's say, designing new material, it becomes particularly important to know what is the mechanism behind what we are observing. So we started to analyze these two materials, potassium copper fluoride and lanthanum manganese, which are cited in the original Kugel-Khomskii paper. And first of all, one has to think about what is the experimental evidence of orbital ordering and Kugel-Khomskii physics. Well, in practice, the ordering appears from just purely electronically. But the expectation is that then the system, through electron lattice coupling, arranged in such a way that reflects this ordering. So it gives rise to a Jahn-Teller-like distortion. And in fact, this is potassium copper fluoride is a system which is a perovskite. And the ideal perovskite would have ideal octahedra with at the center the copper, which is in the D9 configuration, which is the one which is orbitally degenerate. And then the distorted structure predicted by the Kugel-Khomskii model would be one in which one bond becomes long, L, and the other one short, and they alternate in all directions, like it's represented here, which is actually the experimental structure. And on top, I do the orbital ordering, which we later calculated with modern techniques. So this was the evidence, and the same was observed in lanthanum manganese. So here we have a mirror reflection along this plane. So here the long and long are in the same direction, but they alternate in this way, and that's fully compatible with the Kugel-Khomskii model. The problem is that if this is the evidence, it's not so clear that the origin is indeed Kugel-Khomskii, because there is the traditional Jahn-Teller mechanism, which in these materials predict exactly the same type of distortion. So the modes which in the Jahn-Teller mechanism through electron phonon coupling lead to a Jahn-Teller distortion are exactly the same, and therefore the evidence that we are observing experimentally leave us with the open question: what is the dominant mechanism? That's why basically the problem is a chicken and egg problem, where you never know where what is the original, what is the main driving mechanism and what is the consequence. And it's very important to disentangle the two. But as in the case of the true chicken and egg problem, solution can be found, and in fact, that's what I want to tell you about. But let me start, with the line of history. And initially, it was believed that the proof of the Jahn-Teller, of the Kugel-Khomskii model could be found via LDA plus U. In this way, one could calculate the total energy versus the distortion. And for potassium copper fluoride, the first calculation showed that the structure with no distortion is stable unless one adds a Hubbard U, although with the Alto-Fock approximation. So that seems to be an evidence that you need about you. However, this calculation was not quite final because, as was shown later on, you can find also a minimum without the effective U, but the effective U enhances the energy gain. So it's a quite subtle situation where everything is mixed and it's not as simple as it appeared at the beginning. But also, this leaves with some problem. If you have a Kugel-Khomskii model, you expect a transition. And the transition can happen at different temperatures for orbital spins. And it can happen that the orbital is larger than the magnetic transition, but it's somewhat surprising if it's very much larger than the magnetic transition, because the mechanism is more or less the same. And in potassium copper fluoride, no transition was observed at all till melting temperature. The transition temperature for orbital ordering was estimated to be experimentally 1,400 Kelvin or more. A more lucky case was lanthanum manganese, because there a transition was observed around 800 Kelvin. Namely, the Jantella distortion was seen to disappear, and the orbital ordering temperature was estimated as 800 Kelvin, which is larger than the magnetic one, 140, but not as large as in the case of potassium copper fluoride. But nevertheless, it's still quite larger. So one would have to explain this fact if Kugel-Khomskii is the real mechanism. So that's where we started to look at the problem, and we use the modern tools of which we now have, which is the LDA plus DMFT method, which allows us to take into account both the material and the Coulomb interaction in a way that LDA plus U cannot. And all calculations I presented are done with codes which have been developed in my group, which are multi-orbitals and which take into account general Coulomb interaction, and with the aid of our supercomputers in Jülich. Okay, but let's go to the result, which we obtained now quite some time ago. For potassium copper fluoride, the result of the calculation was collected in this picture. So here I show the order parameter, which is the occupation of orbitals versus temperature. 1 means fully polarized, so orbitally ordered. 0 means no orbital order, like the magnetization. And for the real structure, which I labeled here with R, we see that there is no change with temperature at all. That's exactly what experiments see. But then we performed a set of calculations with reduced distortion and identified the true Kugel-Khomskii transition, which is now a curve like this. And this occurs at 350 Kelvin, which is large, but not enough to explain orbital ordering here. So somehow this was the final conclusion that for this system, we could not, so we did have indeed a Tn, which is smaller than the T orbital ordering, but certainly not 1,400 Kelvin. And this could only be achieved if some lattice distortion were in place. And of course, then the natural mechanism one thinks about is the Jantella distortion. But it turned out that not even that was completely true, because even with a Jantella distortion, you do expect at a certain point, Jantella distortion decreases with temperature. You increase the temperature, you approach a transition, a Jantella transition this time, and somehow the Jantella distortion goes away. However, experiment had shown a very unusual structural evolution with temperature, where actually the Jantella distortion becomes larger, increasing the temperature. That's something anomalous. So the Jantella distortion is defined as the difference between the long and the short bond, and divided by the average bond. And we could reproduce actually this result very nicely with GGA plus U, which gives in this context the same result as GGA plus DMFT, as we've shown in a few cases. And we could reproduce this effect. So what was exactly going on? Well, in reality, there is not even the Jantella distortion that dominates this structure. What happens is that the short bond which is plotted here. This is the energy curves as a function of the short bond for different temperatures. The short bond at the minimum is the same for all temperatures. So the ions basically are at touching distance, and what happens, increasing the temperature, the long bond increases. The long bond increases means that it's not a truly Jahn-Teller phenomenon, but instead, there is a competition between free effect, the crystal field determined by the electron-phonon coupling and enhanced by Coulomb repulsion, the Abel term, which is changed by distortion, and the repulsion at when the ions are too close to each other, which we describe the Born-Mayer potential. And only this last term, the Born-Mayer potential, determines that they cannot touch and they stop there. So the actual structure is determined by the competition of these three, which is interesting by its own, because if one can suppress the Jahn-Teller term in a closed shell system, one could have even a transition which occurs at high temperature instead of a low temperature. Now, this you could read in this paper that we wrote a few years ago. But okay, just to come back to our Kugel-Khomskii, this means that potassium copper fluoride, which was one of the two systems proposed, is not actually a real Kugel-Khomskii candidate. There is some Kugel-Khomskii physics, but it doesn't produce really measurable effects. The second candidate was lanthanum manganese. Lanthanum manganese was more promising because a transition was indeed observed at 800 Kelvin. So we repeated the work for that case, and we found a Kugel-Khomskii transition temperature reticle from pure superexchange of around 600 Kelvin, which is quite large and close to this 800. The problem is that when you start to look experiment, then you realize that nothing is as simple as it seems. And indeed, the Jahn-Teller distortions, they only disappear in certain sense, so in the sense that the average crystal doesn't have this distortion, but a small nanocrystals survive, which still maintain this distortion. And therefore, the actual critical temperature is much higher. And what happens at 800 Kelvin is just an order to disorder transition. Okay, we were saying, okay, maybe, however, the superexchange transition drives this orbital order transition by reducing the energy gain for orbital ordering. And to analyze this idea, we then looked at a series of rare earth manganese O3, where the orbital order transition has been measured in the full series, and the temperature actually increases by decreasing the ionic radius. It's not perfect. We did this calculation, and we found that, however, that this trend cannot be reproduced by superexchange alone. There you need the static Jahn-Teller distortion to reproduce the experiment, because the actual superexchange transition temperature is quite independent on the ionic radius in these series of systems. So one cannot ascribe that phenomenon to Kugel-Khomskii physics. So that was a bit the status. We had tried all classical Kugel-Khomskii systems, those that were considered examples of Kugel-Khomskii system, and many others of the same type, and none of them seem to really show evidence of Kugel-Khomskii physics when one looks in detail to the experimental effects. So that's when a few years ago we started to think that maybe we are looking in the wrong place, because these materials are all EG materials, and there is a strong lattice electron coupling. So one perhaps should look where the electron coupling is smaller, like T2G materials. T2G materials also have larger orbital degeneracy, which could compensate for the fact that superexchange is, of course, also smaller. The hopping are also smaller because it's a pi bond and not a sigma bond. However, maybe one could find the ideal place, the ideal spot where Kugel-Khomskii effect could indeed appear. And indeed, one of these systems was lanthanum titanium 3, is the one for which the orbital liquid theory was proposed. So we started from the D1 electronic configuration. And this system, of course, have been studied for a long time, even with DMFT. And in fact, I myself had worked on those in 2004. And we had somehow excluded the possibility of an orbital liquid theory because the A plus DMFT calculation at high temperature showed already basically full orbital ordering with a small crystal field splitting. However, we never looked at a very low temperature regime because, well, at the time it was very hard to do these calculations. And the interesting region to look at would be in this new insight that we gain right above the critical temperature for the magnetic transition. So in a region which is close to the magnetic transition, but where the magnetic transition didn't occur yet. And the idea would be the following: well, we could have a free regime. If the crystal field splitting is very large compared to the critical temperature, roughly speaking, then of course so the order parameter stays always 1 at any temperature, and the orbital which is occupied, which I indicate here with psi, well, this orbital is basically determined by the lattice distortion, so the crystal field splitting. So that's this blue line. The red line is the opposite case, where the crystal field is negligible. That is a more theoretical situation because it never happens in practice. But in this case, well, we have a real transition. So the orbital order parameter goes from 0 to 1, and the occupied state is some other state in general, determined by the Kugel-Khomskii interaction. As I was saying, in the case of the T2G, this state, KK and crystal field are identical, so it's difficult to distinguish them. But as we will see, that's not the case for the T2G materials. And then in between, we have a situation where we have a transition, and if the crystal field splitting is smaller than the Kugel-Khomskii temperature, we would have a transition, so let's say a smooth transition in the order parameter, but a sharp transition in the occupied orbital. So as soon as the super exchange kicks in, then the orbital would change toward, moving toward the expected value for the Kugel-Khomskii model. So that was our idea. So for checking this idea, we had then first to obtain this psi kk, so to derive general super exchange Hamiltonian, which would work in any type of distortion, and then to perform the DMFT calculation for this type of materials very low temperature. So that's the first thing we did. We derived general super exchange Hamiltonians, first starting with the titanate, and then we generalized this work to all kinds of interaction. And the idea here is to perform this perturbation theory in the most general case and project the Hamiltonian by using tensor operators which are irreducible, so that one can indeed identify which element is which and which contribution is relevant for the orbital ordering itself. So in general, we find Hamiltonian of this kind, where this tau are the pseudo-spin operator, which would have both orbital and spin index in the general case. And this coupling depends on the hopping and the Coulomb repulsion. And well, okay, this is some projection which you can implement numerically, but we did the derivation analytically, so you can find in the paper I was mentioning all the tables of these hoppings. And in this way, we can actually analyze what is the crystal field orbital, which would be occupied. So for that, we parameterize the orbital. So now we have T2G with free orbital with two parameters, theta and phi, which we could project into a Bloch sphere. So phi was represented by the vertical line and theta by the horizontal one, so that we could follow, for example, the evolution with temperature from red high to blue low, of a certain orbital. And here, for just for clarity, we will so the field these ones are the Kugel-Khomskii states, and the empty orbital are all for real structure with crystal field. So in this way, we could identify by total energy calculation the crystal field, the optimal angle for the super exchange interaction in the paramagnetic, magnetic, or ferromagnetic structure. We can plot it in our sphere, and we can compare with the crystal field, and we can study the temperature evolution. So that's the result which we obtained for the titanate. So for the titanate, I'm plotting here the calculation of the orbital parameter as a function of temperature for different, for the real structure and for the structure without crystal field. So this gives us the critical temperature, and this is the calculation we're actually interested in. So what happens is that we have a transition just above this blue line, so here, and what we see is that this transition, however, does not affect at all the polarization and the occupied state. So if we look to the circle, they don't move. So here they are all in the same position. They don't move at all with temperature. What we see moving is this curve here. So these are the points which correspond to the orbital at every temperature. But here this is fixed, the same orbital at all temperatures. So there is no actual effect in the orbital as we were hoping to observe. So we are always in the limit in which the crystal field is larger than the critical temperature for orbital ordering. So it starts to become hairy because there is a lot of talking about the Kugel-Khomskii physics, but where are those systems where we can see that? By making this analysis, however, we had an idea to look at different configuration, because we could prove analytically that some of the super exchange terms were larger in the D2 than in the D1 configuration. So perhaps this was the last hope where to find this kind of effect. And for the series of perovskite rare earth vanadium O3, there's been a lot of studies, experimental, claiming that indeed there was a phase, a region of temperature where possible change of structure were occurring very close to the magnetic transition. Actually, these systems are quite complicated because they, these D2 perovskite, they undergo a series of structural transition at low temperatures. So close to this structural transition, which where the system become also immediately magnetic, there were a region where it was claimed that super exchange effect were at play. But of course, as we have seen, in many cases there have been claims of super exchange effect which were proven to be incorrect. So again, I had looked to these systems some time ago, and what we had seen is that at high temperature, orbital fluctuation remain large. So these are the occupation of the different orbital versus temperature. But we never looked to this interesting region I was discussing about. So that's what we did actually then now. So here the same plot I was showing before with the two titanates, and these are the two vanadates. This is the polarization for the real structure. So here we see that this curve is now much lower, so it goes much slower with temperature. But in yttrium vanadate, again, when the transition occurs, basically the polarization is already reached. And if we look to these points on the block sphere, which represent the state for this calculation, they don't change at all. So we see very little temperature effect. However, when we look to lanthanum vanadium O3, that changed drastically, because here we see that the two curves overlap, so the curve is much lower now at high temperature, and the orbital did turn toward the Kugel-Khomskii model. So that is the first time where we see this effect I was mentioning, where the crystal field actually turns around. Do I have 5 minutes? Yeah, okay. So that was very exciting. And in fact, then we analyzed with our tensor the various contributions. And we can decompose now the energy gain due to super exchange in the various irreducible channel. And we could see that in the case of the titanates, there are a lot of terms we contribute, but for lanthanum vanadium, despite distortions, the structure is quite similar to cubic. So this is the red one is the material, and the gray point is cubic. And so this is the nominal contribution. So it makes it more like to an effective cubic system from the point of view of superexchange, although there is strong distortions. And the proof in the pattern was that well, experimentally, a lot of magnetic fluctuation were found above the structural magnetic transition. But what was particularly interesting is that it was a different magnetic structure. So G-type instead of C-type. So if this was indeed super exchange driven, then we should find the same phenomenon in our calculation. So that's what we did. We did a magnetic calculation. And what we found is that indeed in the same region, there is a magnetic transition. And even surprisingly, the magnetic transition is this time above the orbital ordering transition, the TKK that we had found before, exactly in the region right before the experimental structure. So this is the magnetic transition. This is the orbital ordering transition. And the structural change, of course, more or less here. So 50 years after the Kugel-Khomskii model was founded and orbital physics became a big branch of physics, strong correlation physics, we have found a real clear-cut case where you can identify super exchange effects which are clearly there. This is the case of lanthanum vanadium 3, and with the insight we gain, we hope that it will be possible to design other along the same line in the future. The advantage of lanthanum vanadium 3 from the Kugel-Khomskii point of view is that it's a D2 configuration. It has relatively small crystal field and a relatively large magnetic interaction for the specific structure. I came to the end, and I would like to thank my collaborator, Jin Zhang, Eric Koch at the Institute for Advanced Simulation. In particular, all the new calculations were done by Jin, which is a postdoc in my group. And of course, I would like to thank the Supercomputing Center for the computing time that we obtained to make this calculation. And finally, I would like to thank you for your attention.
Thank you, Eva. So we have time for some questions. I think it's just easier if you come down here so Eva can see you and hear you.
Oops, let's see. So thanks, Eva, for this really nice talk. So my question is, if we consider only pseudospin orbital exchange interaction, and then we add some kind of frustration, like let's say geometrical or consider next nearest neighbors, can we end up with some analog of quantum spin liquids for, oh sorry, you here, for Mott insulators? I mean, I was wondering if there's any kind of fluctuation that could lead us to these novel states. But not for spins, but this orbital that appears in second order and perturbation theory for the Hubbard model. Can you comment about that?
Sorry? I didn't fully understand the question. You are asking if can appear...
Okay, so let's repeat. If we start with that effective theory for orbitals, which are kind of pseudospin, right? Mm-hmm. And then if you consider some kind of frustration, let's say next nearest interactions or geometrical ones, and you think that we can end up with some kind of analog for quantum spin liquid?
Yes, of course. Okay, this was, for example, there was this orbital liquid theory, and you can make exactly the same type of phenomenology that you find in a spin case. But of course, as you know, spin liquid are already difficult to find, and orbital liquid are even harder because the system tends to make distortions that somehow quenches these phenomena. But in principle, yes, it can be found.
So there are any kind, I'm sorry, I have one more question. Can I ask it? So we have any kind of exact solution like in the spin liquids in 2 dimensions? Let's say there is any toy model that you can construct, and in order to build some let's say some specific features that are exactly solvable, just to create some theoretical intuition?
Yeah, so for example, where was, so in this paper, it was proposed purely theoretically, an orbital liquid solution for lanthanum titanium 3. As I said, in this material is not realized, but if you could manage to fine-tune the couplings so that they are as described in this model, then you would have a spin liquid, sorry, orbital liquid. Yeah.
Okay.
So in principle, it's all there. The problem is always how to make it work in a real system.
Yeah, you're completely
right. How to make it realize in a real system.
No, I can see the energy scale is not so really accessible, but I'm just wondering, if there's anything that, because I'm not really expert in that spin orbit interaction system, but yeah, I think I have to learn something on it. Thank you. This was enough.
We still have some time for more questions.
Hello, I'm Marcello Civelli from Paris-Saclay. Thank you for the talk. Just very naive question, sorry if perhaps it's too naive. In many multi-band system interacting with a super exchange like this, I'm thinking to iron arsenide, for example, people has been discussing a lot about possible orbital selective mode transitions. Is there a connection with this orbital polarization physics? Or is a competing order, or a possibility related to the structural change?
Yeah, orbital selective mode transition
in particular in the vanadates. I have not seen discussing this in vanadates actually so much.
Okay. There is. It depends what you mean by orbital selective mode transition. So in the vanadates, of course, there are 2 orbitals which are occupied. So in the orbitally ordered phase, and one is empty. And if you have an insulator, so you could say, okay, it's orbital selective, but it's a bit a trivial case of this, in which one is empty and 2 are occupied. Initially, it was proposed for the rutanates, where you have a default configuration in the T2G shell. And then the idea was that there was one of the orbital remaining metallic and the other 2 going insulating. The reason was there that the bandwidth of the 2 orbitals, so because of the layer structure, the bandwidth was much smaller, so you would have this configuration. So with metallic and insulating in different channels. That, however, never proved to be correct. So there was a lot of discussion. I worked on that also. If you make a realistic calculation, this does not happen. So you have a fully orbitally ordered solution, which is not, which is fully, so some orbitals are empty, and the other one are then, they have a gap. And so it's not really exotic type of, let's say, orbital selective case. And the orbital selective mode transition has been studied a lot in the context of the Rutanate. Now, so it's related to this orbital polarization, but if you want the case in which you have orbital ordering and orbital selective transition is a bit trivial because it's all bands which are either empty or full, and it's not the most interesting case
about
where one is metallic.
my understanding about orbital selective is that, I mean, it's not just a question of having one band empty and the other full. The band that is going empty is actually losing spectral weight completely.
So let's say the interesting picture is when one band stays metallic and the other one goes insulating. Then only one orbital goes insulator, and this was what was proposed for the Rutanates. But that does not happen in practice. So, but it's more, it's different from what I'm talking about today.
Okay, thank you very much.
So I think we now have to move on to the next talk. So let's thank Eva again for this very nice talk.
Thank you again for your attention and for the kind invitation.
Thank you, Eva.